Welcome everybody to the online seminar series, Machine Learning Needs Mathematical Optimization. Today we have the great pleasure of having Antonio Frangioni from Universidad di Pisa, Dipartimento di Informatica. He is a full professor there, and his main research interest is large-scale optimization. He uses both continuous optimization and combinatorial optimization to address these problems. He has worked in many fields of application, including energy, transportation, and telecommunication. But he also shares interest in other areas, such as artificial intelligence and machine learning, and he studies the role of mathematical optimization over there. So it's really at the core of this online seminar series. Antonio has published with many co-authors in top journals in the field, such as Management Science, Mathematics of Operations Research, IAM Journal, Optimization, and etc. He is involved in many research projects funded nationally, but also European activities, such as the Horizon 2020 Marie Curie training network MINOA and the former cost action mathematical optimization in the decision support systems for efficient and robust optimization energy networks. We are extremely pleased to have you here, Antonio, and the floor is yours. As I said, 45 minutes, and then we leave some time for questions. If the audience has a very urgent question, please put it in the chat, and then I will read it to Antonio. Thank you very much, and the floor is yours.
Okay, thank you very much, Dolores and Emilio, for thinking about inviting me. It's a real pleasure to be here. I've always liked to, be in the middle between different fields, and even much longer, much before that, machine learning came back in shape. I was sort of fascinated by the field. Lately you cannot basically go anywhere without saying something about machine learning. And so it was, I think, the right time to try to recover some of my former ideas. And this particular research I will be speaking of is actually the thesis of Gabriele Ionmazzo, who is going to present another part, basically, of this talk. I would say the real part of this talk with the real results later on in this seminar, but also with my good friends Claudia D'Ambrosio and Leo Liberti at École Polytechnique. This has been, I think, a nice experience for me, and I'm happy to try to share that with you. I will try to keep the talk short. So first of all, why we really wanted to try to solve this problem, and then what problem we try to solve, which I think it's an unsolvable problem in theory. So everything you do is good, because the final object is not really reachable, so you can just approximate that, and this is what we are trying to do. I will argue, and I hope you will agree, that putting together machine learning and mathematical optimization is the right way, or possibly the only way, to go about solving this problem. And while the main idea is reasonably simple, in fact, the implementation is not. And this is where poor Gabriele has sweat a lot in his last 3 years together with us, and we did get some results, some of which I will give you a brief glimpse of, to try to share the fact that the idea might work, and Gabriele will tell you more next time. Okay, so the motivation is that optimization is hard. save, of course, the remote possibility that someone would prove that P is equal to NP, which would be a real shock to all of us. All problems that we need to solve are difficult. And there is a sort of strange chasm in the theory, because basically the theory tells you that all NP hard problems are equally difficult. But in fact, you know by experience that problems are difficult because different aspects of the problems, of different problems are difficult. So it might be extremely difficult to find any feasible solution, or you may have plenty of solutions, but finding the optimal one can be extremely hard. In order to solve the problem, you will need to solve some problem that would be easy were it not so dramatically large, or the problem can have some specifically nasty components, functions, or parts that are in themselves hard to compute. So I think the NP completeness or NP hardness story is that however you go about solving difficult problem, you will hit a wall sooner or later, but you typically hit different walls depending when you arrive from different directions. And so in order to be able to do anything, basically the idea is you cannot just hope that one solution approach will always work. So you will have to look at your particular problem and see where your particular problem is hard to solve and do something for your particular problem. This is true basically for all difficult problems, but in particular, general purpose solvers, that are the ones that we are sort of interested here, are particularly troubled by this, because basically if you need to solve some very large class like mixed integer linear, or even worse, mixed integer nonlinear programs, then in order to make something that solves any of these guys, or at least tries to, you really have to put in there very many different things. And you know, bounding techniques and relaxations and column generation and heuristic preprocessing reformulation. Every working algorithm for a large class optimization problem is really many algorithms that have to talk to each other, and where you have to find lots of trade-offs between how much you spend on this part and on that part, and if you do this part in this way or that way. Okay. Now, I am particularly interested in especially large and nasty problems that require especially large and nasty solvers, for which I have been developing a system that is pointed right there, but the system is not the story of today, so I will avoid to tell you anything more. Today is more about standard, let's say, run-of-the-mill general purpose mathematical optimization solvers. Okay. And the point is that any good solver has very many algorithmic parameters, and we all know that when your specific class of problems comes to you from reality, and you have to really try to solve them, typically you have to start and do some parameter tuning, which is crucial for the problem to be solved in reasonable time, if this is at all possible. So this is something that we might relish, in that it's one of the reasons why we as optimization experts might be in demand. But the truth is that it's a hard, mostly manual process that is mostly trial and error, whereby you try to infer something by looking at some solver logs and knowing something about how the solver, what the solver is doing, which for some solvers you only know something but not the whole story. And you have to look at your specific solver, and this has to be specifically, let's say, instance by instance, or at least I mean specific class of problems by specific class of problems, because you can just say I have the optimal parameters for every milk, because no such thing exists. Okay, and we know. So basically what we have here is a process whereby we have, and I mean it's plain to see that this is basically a meta optimization problem, and this is the way we will put it. okay, whereby in order to solve the optimization problem, you have to solve another optimization problem before whose variables are algorithmic parameters of your solver, and these are many. And typically, while we use our sophisticated mathematical optimization techniques for the solution process, for the second solution process, we only use experience and, well, a little bit of support, but not much from the tools to do the first thing. And so basically, there's a scope here, I would say, to automatize this experience-based process. And I mean, I think that most of you would agree that this is one of the places where machine learning really shines. So I mean, it basically shouldn't be anyone's surprise that we could try to use machine learning to do parameter optimization. Okay, so formally speaking, just to put some things on the table, the algorithm configuration problem has been known since 30 years or more, I would say. Has been defined since 30 years or more. And formally speaking, you have some algorithm for some problem, and the problem is typically an infinite set of different instances. And you have a configuration for this algorithm, which is a finite vector of parameters. But what will be important in all this talk is that this is finite but not small. So you have many parameters. And these parameters define a set of feasible parameter configuration, which is at least combinatorial in the set of parameters. So it's typically very large. And I mean, it can also be infinite because some parameters might be continuous. And also you have logic relationships between parameter of the kind, if I'm using the barrier method, then I could use either primal or dual crossover. But if I'm not using the barrier method, this does not make sense. Okay, so there is some logic in the choices that you can reasonably take about your algorithmic parameters, and this choice is one of the reasons why we basically went for the direction we took, as I will tell you. Then you have a performance function that measures the efficiency of the process. And this is also non-trivial. You have to take all the efficiency of your process and try to come up with a single number that describes how good this is. We will take some shortcuts, but even with the shortcuts that we have taken, you will see this is not completely obvious. So the choice of the performance function has might have to be discussed, or there could be some ideas like I have multiple performance functions, which could also be possible, but creates other complications. So we will stick with one performance function. And I mean, the algorithm configuration problem is basically, it's very simple. Once you get any instance of your problem, a fixed instance that you want to solve quickly, find the optimal configuration, and of course, hopefully a good configuration that provides the solution with optimal performances. And it's clearly, as I said, a meta optimization problem where the configurations are your variables. Sometimes this problem is called the algorithm selection problem, typically imagining that you have a portfolio of algorithms and each algorithm is a configuration. Well, I mean, typically this means that your set of configuration is not very large, whereas our one is. So I am convinced that this problem is extremely hard, undecidable probably, in this very general formulation. And although we look at it in terms of mathematical optimization problems, it's clear that basically what you are trying to do share a lot of similarities with other things. Hyperparameter tuning in machine learning is clearly one, but also my idea is all the time you have to take decisions based only on some models, on some idea of what will happen that you have constructed painfully out of past experience. Whatever we do here can clearly be solved in this kind of treatment. Okay, so how do you, what do you want to do? What you want to construct is basically a function, okay, that we will recommender, and the function is something that given at the instance tells you back the configuration of the instance. Okay, and now this function is clearly complicated to construct. Okay, because basically, in order to do that, when even if the new instance is fixed, in theory, you have to look to the entire configuration space. And the entire configuration space is large. And not only that, typically looking at one point of the configuration space would require running the algorithm. But running the algorithm for us really is a black box. And I mean, you typically cannot run the algorithm many times and then say, okay, this was the faster one, so take that one, because this defies the purpose of the fact that I want the solution quickly. Even assuming that you can do that, because if you think, again, personalized medical treatment, if you're given the wrong medicine to the patient and the patient has died, this is not something you can undo and say, oh, well, that was a bad step, I would do better next time, okay? So clearly what you have to do is you have to construct a model that encodes some knowledge about your performance function and try to use the model to help you solving this problem. I mean, for algorithms, we all know complexity theory, but we all also know that worst case complexity theory is most of the time hardly any useful. And average case complexity theory, even if it works, is, well, it doesn't work too much either, and it's also much more complicated to get. So clearly the way out for this is a data-driven approach. So do experiments, run a learning phase on a training set of pairs, which is the important part, instances configuration, and out of this construct a model that can then be used for the recommender. And also let me mention quickly that once you have constructed the model, if you have time to do more learning, you can use the model itself. And this is typically done to help you guiding in the exploration of the configuration space. So a very quick view of the thing. So you have a learning process that gives you a model out of which, when the instance comes, in the recommendation phase, you can get an answer. And if you have time, and there will be some sort of budget of effort here that I don't want to discuss, but it's an important subject, you may also get back, having gotten some more, once you run having gotten some more information, you can improve your model and do this kind of play. So, in fact, there is, as you can really imagine and know, a lot of literature about how this kind of things are done. And there are many different approaches depending on several things, like what the model is, and so how the recommender works. Whether you really want to work instance by instance, or as in many cases, you really try to choose a configuration that works reasonably in all cases, so a per problem thing. And also whether this recommendation phase is done once at the beginning of the algorithm and never thereafter, or you can repeat it at different stages of your algorithm, incorporating dynamical information during the solution process. And let me mention, we are in an offline approach, but each time you have an offline approach done, you can really think of using it as the basis for an online one. And so while I won't discuss it, I also see this as a clear possibility, provided, of course, that the trade-off between the time it takes you to do the recommendation and the benefit that you get is working, which is absolutely not obvious. So there are, I would say, basically 3 types of recommenders that you find in the literature, plus some special cases or strange mixes. One is where you have a process that tightly recommends a configuration. Okay, and this is something that machine learning would typically do for you, in particular things like neural network or the like. A problem in this is that not always machine learning is good at managing the combinatorial constraints that we have on our space of configurations. So our favorite approach, let me tell you immediately, is the one where we use machine learning to just compute an approximation of the performance function. And once you have computed the approximation, our way of choosing the best configuration is just that of optimizing over this approximation, hoping that this approximation will give us relevant information to approximate the other thing. There are other ways. Typically, one thing that is done is to find some set of representative instances for which you find good configurations in some way, and then basically try to find which of these representative instances is closer to your configuration, to your current instance, and use the best configuration for this representative as the best configuration for your instance. And there are also some things in the middle, that I don't really want to discuss. And at the end of the slides, there is all this literature if you are if you are interested. And basically, what I would like to show is that predictably most of the work is based on offline per problem approaches, whereby you try to find one good configuration and that's it. But there is also work, comprised as arts, on the per instance version. And we will do per instance. So what do we do? How do it work? So of course we make some assumptions, and I will list you 3 assumptions here. The one is that we can express in a way that is reasonable for basically any general purpose optimization solver the constraints over the set of configurations. So let's say our configuration are just represented by some long binary vector with some linear constraint on it. Then if we would have continuous or general integer parameters, that this would be achievable. Almost all of the things I'll tell you, but not exactly all, will not change a lot if this happens. The other thing is that you have to decide on a performance function. And what we did, for good reasons, given the kind of problem that we wanted to solve, is to fix a time limit and optimize the gap. But as you will see, this also requires to some shenanigans at the time, and because this happens to us, when actually you're not able to get any solution. And this you will see has an impact. The assumption I'm mostly worried about is that you know a good encoding of your instance in a finite set of features, real numbers. And this is, I think, the most complicated part that we really are not, really trying to solve. We assumed we did that in a reasonable way for our problem, and we hope that there will be ways to do this in reasonable ways for general problems, but I'm not really sure I know a way that is really convincing for doing this. So at least this might remain a manual part of the process for a long time. But of course, if any of you know some promising approach
presentation has gathered a lot of a big audience and many questions. So thank you so much for coming today, and thank you for offering yet another presentation next week through your student, Gabriele. We hope to see you soon, and to the rest of the audience, maybe see you next week at the Young Online Seminar Series, Machine Learning Needs Mathematical Optimization, with 3 interesting speakers next week. Thank you all.
Thank you, everyone. Goodbye.
Thank you, Antonio. Great talk.
Yeah,
Thank
marvelous.
you.
Yeah, I have enjoyed a lot. It's